Now, how do we interpret the coefficient for an interaction term? This was the code that we used to create our model with the interaction term. And this is the results. We have an intercept of 11, a coefficient in front of tip of just under 2, a coefficient for credit that is a -7, and an interaction coefficient of 1.68. Now, when I use those coefficients to write this model, to write the model predicting fair, this is what I get. But how do I interpret what this means? I have this coefficient in front of tip, a coefficient in front of credit, and then I have this coefficient in front of tip times credit. So I want to give you an example that will show you exactly what's going on in the simplest of cases, as I always like to give a simple example. So remember here that credit is binary. It's either 1 or 0. People pay in credit or they don't, and if they don't, they pay in cash. So let's consider, since credit can only be 0s or 1s, let's plug in 0s and 1s for credit and see what happens. Consider if you were to plug in a 0 here, then this would be 7.12 times 0, and it would be eliminated from the model. And over here, 1.68 times tip times 0 is going to eliminate that entire term from this model. So if you consider credit equals 0, you're actually getting fares predicted by the intercept plus only 1.67 times tip, because this would disappear if credit is 0, and this would disappear if credit is 0. Now let's consider when credit equals 1. We'll still have the intercept 11.72, and over here credit will be 1, so we'll be left with just the number -7.12. Well, if I've got 11.72 and -7.12, I could just add those numbers together. I would also have 1.67 times tip and then 1.68 times tip times 1. So I can add those two numbers together and multiply them by tip. So I'm really getting an intercept of 4.6 plus 3.35 times tip. So what I think is extremely interesting for this simple example is that I can see visually that I have two different intercepts and two different slopes. I'm implementing two different models, one for when people pay in cash and one for when people pay in credit. Not all cases are going to be as simple as that one, because sometimes we'll have an interaction of two continuous things. But we can see changes in each of these models in lots of ways. We can first look at the R-squared. So here's just tip in a model, here's tip and credit, and here's tip plus credit plus their interaction. The R-squareds will differ. In the first case with just tip, it's about 36%. In the second case with tip and credit, it's about 43%. Now when we add the interaction, it really doesn't go up by that much. It goes up from 43.39% to 43.49%. Not a huge difference in the R-squared. So that's starting to make me wonder, do we really need this interaction at all? So is the model actually improved? Well, let's look at the prediction errors with and without interactions and compare. Just like we would compare the training to the test data and make a decision about stability and accuracy, let's talk about improvements. So we'll take the mean absolute error for the model with just tip, for the model with tip and credit, and for the model with tip, credit, and their interaction. It looks like in all three cases, we're still going to be off of our fair prediction by about $5-ish. When we go from just tip to tip plus credit, we're improving our estimation on average by 60 cents, which is great. But when we add in the interaction, we're only improving by an additional penny. So that's not so great. I'd say it's worth adding credit to this model, but it's not necessarily worth adding the interaction. We're adding a lot of complexity and we're not really getting a lot of bang for our buck. We could also look at the standard errors and they all look relatively similar. So they're telling the same story as what we've already decided, that maybe we don't need the interaction here, but I want you to keep it in mind for future use. A good question for us to answer is it okay for us to be off by $4 when we make a prediction of taxicab fares? So conclusions for interaction terms are just give them a shot. Make guesses about what interaction terms might be important and see if they're significant when you add them to the model. They can be interactions between any types of variables. One of them does not have to be binary. You could have interactions between continuous things. The only reason I use the binary variable here is because it's easy to understand an interaction when you talk about binary variables. You can use the significance of the coefficient in the interaction term, the R-squared, and the prediction accuracy to all make judgments about whether or not to keep interaction terms in the model.